So in our previous lab, we found that in order to understand an object's motion, it's good to have data on where it is and when it is, position and time. And you can figure out all sorts of interesting things like speed and changes in speed from that data. There was a problem with our data in the last lab, though, and it really limited how much of a conclusion we can draw. And basically, there wasn't enough data. Now I'm going to have to show you the graph from the last lab to help you see what I mean. I want you to zero in on the graph of crawling, which is the one that's in black, second from the right. Notice we drew a best fit line on it. And in the previous lab, we explained the fact that a lot of the points were off the line. This one occurred earlier than the line would have predicted. This one occurred later. By saying that those were error, that someone just stopped a watch too soon and someone stopped it later. But that's an assumption. Drawing a best fit line, you are saying that I think the slope of this graph should be the same the whole way down. And since slope is speed, you are saying that this object moved at constant speed. Well, did it? Did this kid crawling in the hallway move at constant speed? We'd have to think back to what it looked like, but I've seen a lot of kids flopping around as they try to crawl down the hallway. So it may not have been error. This could have been a kid speeding up, which would make his graph get steeper, and slowing down, which would make his graph get shallower. How would you tell the difference between bad measurement or just simply non-constant motion? Well, the answer is you need more data. We have one data point at 4.5 seconds, and the next doesn't come till 11.5 seconds. We would need data points for all these times in between. And I think you see what the problem is there. We could do that, but that would involve having a lot of individual students timing. And it would get costly in terms of resources. We could have a class of 22 kids measure one kid moving. So we're going to have to think of some way to collect more data. In addition to there not being enough data, and there's a lot of times we didn't measure for, there's another reason that we can't simply have a bunch of people time a motion. We can't physically get 22 people, but what if this was the motion? I've got this angry bird. Throw it up and let it come down. It was only in the air for about half a second. If I wanted the information on that, which is probably interesting, how are we going to even time that? Its motion was faster than human reaction time. So those two things added together, we can't have 22 separate timers, and we have to time very quickly, mean that we've got to find a way to collect data automatically. And that's what the point of this next lab is going to be. Now, we want to keep this lab as simple as possible, so we're not going to have any objects with strange motions. They're going to move at constant velocity. So these little cars are actually really helpful for that. I'm going to show you what they do in just a second. So these cars do just one thing. They move at constant velocity, and one moves slow, while the other one moves fast. And because they move at constant velocity, we do expect their motion to generate straight line position time data. So that'll let us focus in on how we can make lots of measurements in a short time period. So this thing here is called a ticker tape timer, and it's a good way to generate lots of position time data. There's a hammer which is hooked up to the electricity that comes out of the wall. And in the United States, the electricity coming out of the wall changes its direction 60 times every second. And the hammer just moves along with that. That means every second it whacks the paper 60 times. The paper is free to move, can slide. So where the hammer's whacking the paper is going to change. And when it whacks the paper, it hits this inked up circle underneath, and it leaves a dot. So what we're going to do is tape the paper to our cart, and that is going to drag it, and it's going to cause a pattern on the paper. What that paper looks like is going to then give us some information about position and time. So we're going to run this with blue ink for the slow cart and red ink for the fast cart, and then we're going to compare our data. So this is the data from our slow cart, which we recorded in blue ink. Now we'll do it with our fast cart, which will be in red ink. So if we look at the data from our slow cart, we see there's a couple of regions. Remember that each of these dots is 1/60th of a second later than the dot before it. And the reason they're not all right in the same place like they are at the left side of this tape is that the cart started moving. As the cart moved, it dragged the paper, and that meant that the hammer hit the paper in a different place each time. So at first, they were all on top of each other, and then they started to spread out. And the reason for that is the cart was getting faster and faster and faster until it reached its cruising speed, and then you could see the dots are evenly spaced. So that's the part we're interested in. That's the part where the cart is moving at constant speed, where the dots are evenly spaced. Let's compare this to the fast cart. You can see very similar pattern, but the dots are spaced out more. And the reason is the cart moved faster, and therefore it started dragging the paper out quicker. So the hammer, although each dot is still a 60th of a second apart, the paper moved more in this 60th of a second than it did when we were looking at the slow cart. The cool thing here is that every single one of these dots is now a data point. It was collected automatically. We know the time. They're a 60th of a second apart. And all we have to do to measure the distance, how far the cart had traveled, is to get a ruler and measure how far apart the dots are. So let me show you how to do that. So I've got the data for the slow cart again. And we're just interested right now in the times when the cart was going at constant speed. So this beginning time, where it starts out with all the dots on top of each other and they start to spread out, that's not really the part I'm interested in. I want you just to find where the dots appear to be evenly spaced, and I'd like you to draw a line across the paper. And we're going to label that as 0. And then I'd like it if you could go ahead and just count all the dots you have left after that point. So you could just, you don't have to write down all the numbers here, but every dot gets its own number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to go through and label all these dots. So here I am. I have all my dots labeled. And in theory, I could actually put 91 individual data points on my graph. That's a little bit of overkill, so I'm going to just have you guys shoot for 9 to 10 points. So I'm going to do every 10th dot when I go to make my graph. So the point of this lesson now is going to be to try to figure out how to get distance and time data from this. And you actually just got the time data already by counting. You got to remember that each of these dots is 1/60th of a second after the previous one. So this is not 5, it's 5/60ths, 10/60ths, 15/60ths. We will convert back into seconds later, but let's just use the unit of dots as our time data. So I'm going to collect every 10th data point going up to 91. So as I go to make my t-chart, I'm going to write time and position. And time is going to be measured in dots. X, position, is going to be measured in centimeters. So I'm going to do dot 10, or yeah, dot 10, dot 20, 30, 40, 50, 60, 70, 80, 90. So if you had 70s, or 70, you could count by 7. That would get you 10. If you had 110, you could count by 11. But we just want 9 or 10 data points. How do I get position? Position is how far away you are from the beginning. So I'm going to go to dot 10. I'm going to take my little ruler, put it on 0, and go to dot 10. That is 2.3 centimeters. So you just read off the ruler. It tells you how far the tape was pulled. This is the only tricky part. Dot 20, I don't remove the ruler. I leave the 0 on the 0 mark. So I just go out to dot 20 and I look down, and that is 4.9 centimeters. So I won't bore you and make you go through all this, but just wanted to point out I only had 20 total points for my fast cart. So instead of counting by 10s, I'm going to count by 2s. So 2, 4, 6, 8, etc. So here's our data that we want to compare. And as you can see, they range over very different amounts of time, up to 90/60ths of a second for the slow cart and only 18/60ths of a second for the fast one. We'll draw our axes on graph paper. So we'll have time, and don't forget the unit, this is dots. Time in dots, and then this one will be position, and the unit is centimeters. So I'm just going to go ahead and graph my 2 data sets, and we'll see what they're showing us. So there's our 2 data sets. They are both quite linear. We could draw a best fit line through both of them. Try to get equal number of points above and below. And we are going through the origin because we definitely started at 0, because 0 is just the first dot we consider to be constant velocity. I could have you get the slope manually. In some classes I might do that, but what I really want to show you guys is how to use spreadsheets to accomplish the same task. So that's going to be the next thing we do. One thing that should be obvious, and hopefully you guessed it, is that the faster cart had the steeper slope, and that is indeed what we saw.